Section 7.1, Exponential Functions and their Graphs. In this section, we are going to look at the characteristics of exponential functions, graphing exponential functions, and solving the basic or the elementary exponential equations. Let's take a look at the characteristic of the exponential function. By definition of the exponential function, first we're going to let a be a fixed positive real number not equal to value 1, or in the notation is a is greater than 0, a not equal to 1. Based on the real number line, we start at 0, and then the value a start at any value on the right side of 0, skip the value 1 and keep going in the positive direction. In this case, the exponential function with the base a is the function f of x equals the base a to the power x. Note that if a not equals 0, then a to the power 0 equals 1. That means the y-intercept of any exponential function, regardless of the base, is 0, 1. That means any graph of the exponential function gonna pass the y-intercept at the point 0, 1. Next, exponential functions fall into two classes depending on the value a, as we use the real number line to explain the nature of the a value. So we have the case 1 when a between 0 and 1, case 2 where a is greater than 1. So split in two cases. Case number 1, when a between 0 and 1, the function f of x is a decreasing function. That means when x approaches negative infinity, y is approaching positive infinity. At the same time, when x approaches positive infinity, the y value approaching the value 0. For case number 2, if a is greater than 1, the function is an increasing function. F of x approaches 0 as x approaches negative infinity, and f of x approaches infinity as x approaches infinity. By explaining in the direction of the xy value, x approaches negative infinity, y approaching 0. Where x approaches positive infinity, y approaching positive infinity. This will give us that the domain is a set of the set of real numbers, or the interval notation from negative infinity to positive infinity. The range is the set of positive real number, or in an interval form starting from positive side of the 0. Now we're gonna look at graphing exponential functions. An exponential function, like other function, that can be transformed in ways that result in a graph being shifted, reflected, stretched, or compressed. It often helps to graph the base function before trying to graph the transform one. Let's look at the example. For the first one, we're going to sketch the graphs of the following exponential function. Part A, f of x equals 2 to the power x. Recall the domain of the exponential function is the set of all real numbers. The range of the exponential function is the positive real numbers. So we're going to adjust the graphing scale, like the x can be negative, can be positive, can be 0, and the y gonna be a positive value. For this one, the base is 2, or a equals 2, which is greater than 1. It means the graph is an increasing graph. We're gonna construct the t-table, x and y, where y equals 2 to the power x. If we do the midpoint at 0, so we're going to go backward, -1, -2, forward 1, 2, and then compute the y by, let's clean this up real quick. Okay, the base is 2 to the power -2, which is 1 over 2 to the second, or 1 over 4, or 0.25. The next point of the x is -1, so 2 to the power negative first equals 1 over 2 to the first power, or 1/2, which is 0.5. Next value of the x, 2 to the power 0. 2 to the power 0 is 1. Next one, 2 to the first, which is 2. 2 to the second equals 4. So we're going to form the order pair for our convenience to plot on the xy plane. I'm going to make the table stretch a little bit here. So x negative 2, y 0.25, x negative 1, y 0.5, x 0, y 1, x1, y2, x2, y4. As you see, we have the y-intercept over here. Okay, from the graphing area that's given to you, it's the x scale looks okay. The y scale, since from the table, the maximum is 4 and the minimum is 0.25. I'm going to adjust the scale a little bit, make it bigger than what we have here. So also in an x direction. So ignore the negative 5, negative 10, 5, 10 here. We're going to rescale the graph area. So I'm going to go by, instead of 5, going to be 1. Instead of 10, going to be 2. This is negative 1. This is negative 2. For the y direction, since the maximum is 4, I'm going to go by every 2 increment as 1. Ignore the 5 here, and then 3, and then 4, and then 5. So we have enough, large enough scale to see the clear graph. So the first coordinate, negative 2, 0.25, negative 2, 0.25, which is a half of 0.5. So I'm going to be down here. Negative 1, 0.5, 0, 1, 1, 2, 2, 4. Now we have the exponential graph of the function f of x equals 2 to the power x. It's called exponential. It's the increasing graph. All right, the next one, we have the base. A equals 2 over 3, which is between 0 and 1. This we're gonna get the decreasing graph. Generate the t-table the same as before. So x here and the y, which is 2 over 3 to the power x. X negative 2, negative 1, 0, 1, 2. Y gonna be 2 over 3 to the power negative second. The power negative to the reciprocal with the power positive. It becomes 3 to the second over 2 to the second, which is 9 over 4. Next one, 2 over 3 to the power negative first, or 3 over 2 to the first power. Another way we say we have 3 over 2, which is 1.5. Next one, 2 over 3 to the power 0, which is 1. 2 over 3 to the first power is the same as 2 over 3. And the last number, 2 over 3 to the power second, which is 2 to the second over 3 to the second, or 4 over 9. 4 over 9. And then for our convenience, we're going to change the fraction form into the decimal form. So we'll use the coordinate easier in the graphing area. So 9.5, that is the 9 over 4 is 2.25. So this one could be negative 2, 2.25, negative 1, 1.5, and the next gonna be 0, 1, 1, 2 over 3, which is 0.67 approximately. 2, 4 over 9, that is about 0.44. Okay. As we get in the order pair forms, the max, the min, I'm going to adjust the graphing area like before. Instead of negative 5, going to be negative 1, negative 10, going to be negative 2. 1 and 2 for the 5 and 10. And the maximum for the y value from the table, which is 2.25, we're going to have to adjust a little bit. So I'm going to go with every 4 mark is 1. 1, 2, 3, 4, can be 1. Ignore the 5 and 10. Just for our convenience, you can scale as appropriate, okay? So the first point, negative 2, 2.25. This is 2. So 2.25. So area 1 mark here is 0.5. So gonna be somewhere up here. And then negative 1, 1.5. 1.5. 0, 1, which is the y-intercept. 1, 0.67. That is a little bit more than a half. Right there, and then 2, 0.44. Gonna be somewhere here. And now it looks like it's red line, but not. It's not. It's just the scale that I readjust it, make it look like magnified graph of the decreasing exponential graph, like that. And now we get the graph of the function gx equals 2 over 3 quantity to the power x. For this example, in which direction and how many units would the graph of f of x equals 3 to the power x be shifted to form the graph of gx equals 3 to the power x minus 2 plus 4? Let's analyze the problem. From what we have here, 3 to the power x minus 2 affect to the x area. So that means it's going to shift to the right side 2 units, where added by 4 on top of the exponential term. So that means the graph is shifted upward 4 units. Therefore, we're going to summarize it as this graph shifted from the basic graph to the power x by horizontal shift. That means go to the right 2 units. And vertical shift upward 4 units. So we have the basic graph, 3 to the power x. The graph is shifted to the right 2 units, and then go up 4, 1, 2, 3, 4. So that means the graph gonna be something like that. So the y-intercept 0, 1 now becomes the point that shifted to the right and go up to be at the point 2, and then go up 4. This is 5. So go over here 2 and go up 4.